from Northeastern University. Good.
Right. Right. Hello, everyone. Wow. So before I start, I'd like to thank the organizers for giving me this wonderful opportunity to be here and share my work with you, especially Jan. Thank you. So today I want to give you an overview of the recent developments in my group in terms of developing a new toolkit to calculate spectral functions and thermodynamics for strongly correlated materials using neural network quantum states. You've heard already a lot about neural network quantum states. We know that this is a new variational approach to calculate ground state wave functions, but I want to give it a different spin, let's say. No problem. Have to do mine. Anyway, so before I start, I want to acknowledge my collaborators, basically my former student, Doug, who's now at UPFL in Giuseppe Carleo's group, Hongwei Chen, who's now working in Microsoft, making more than twice my salary, and Philip Weinberg, who's now the QA, probably also earning more than me. And the work I'm going to show today has been published in those references there, and I'll be happy to share them with you if you're interested. So what is this talk about? So first, of course, I need to clarify that I'm a computational content smart person, and I'm going to be talking about computational methods, but since this is a very eclectic audience, I don't want to spend too much time into technicalities. I want to focus on the main message. But basically, what we do in my group is basically we focus on two particular areas that I think, this, in my opinion, are two of the most pressing challenges in computational quantum smart theory. One is to find unbiased methods to study strongly correlated systems in dimensions larger than one. In 1D, we know we can use DMRG, and in 2D, we have a much richer physics that the time being is pretty much still quite out of reach in many cases. And we're talking about spin liquids, high TC, transition metal oxides in general, heavy fermions. And quantum Monte Carlo works really well, as we've seen, but for cases where we don't have the same problem, or the same problem is very small. And the promising area to tackle these problems is using tensor network methods, such as generalizations of DMRG to higher dimensions. But in the past few years, we've seen a lot of progress being done by means of using neural network quantum states. So I'm going to tell you a little bit about that today. I'm not going to be talking about the other work we are doing in my group, which is non-equilibrium phenomena and time-resolved spectroscopies. So cutting to the chase, well, the problem we want to tackle is the so-called representation problem. We have a quantum mechanical wave function that has a large number of degrees of freedom, let's say spins for simplicity, that can be pointing in, say, up and down directions. And what we need to find out is all those coefficients psi there, right? So we have 2 to the n possible spin configurations. We have 2 to the n coefficients to learn. And of course, this number of coefficients, the number of coefficients grows exponentially with the number of spins. And we know this is a very challenging problem, basically out of reach for modern computers. And so the idea is to use a variational solution. And the variational solution consists of basically parameterizing this coefficient psi in terms of other coefficients, alpha, that are going to be our variational parameters, right? Alpha 1, alpha 2, alpha m. So we have m of these parameters, and this is we assume that this number is very small, much smaller than 2 to the L. And so what we're going to do is propose a functional form for this side, and basically a function that depends on these alphas, and try to optimize these parameters with respect to these alphas. So in a nutshell, what this comes to be is basically, we can think of our variational wave function as a black box that takes as an input the spin configuration and spits out a coefficient of that spin configuration. And this black box has a number of knobs. These knobs are our variational parameters that we can tune, and we can adjust them in such a way that we approximate the correct size as close as we can. And this can be interpreted also as a compression algorithm, if you will. So we're going from a space of 2 to the L parameters to a much smaller number of parameters, m. And the wave function that we can represent with this black box approximates the exact wave function. And hopefully we can get this pixelation to go away and adjust the wave function as close as we can to the exact. So one way to visualize this is to think that we have our Hilbert space with all the possible wave functions. And we have a subset of states that lives in this bubble, which are the variational states that can be represented by this wave function. And we can make this bubble grow larger and larger by maybe changing the specific functional form of psi or the number of parameters alpha. In reality, the picture is more like this. It's more like a percolation, right? It's not like a bubble. This wave function explores my entire Hilbert space. And imagine that my exact wave function is in one of the purple regions. The idea is to get this percolation pattern to get denser and denser and approximate this wave function as close as we can. So obviously, not all states are exactly represented, can be exactly represented by these variational states. Some can be represented better than others. And this property of being able to approximate any arbitrary state by a variational wave function, we call it expressivity. How expressive this wave function is. How close we can get to an arbitrary many-body state. In the following, I'm going to focus on quantum spin systems because this is our sort of C elegans. We use this as a benchmark. We have a lot of exact data to compare to, especially when we don't have frustration. We have very accurate Monte Carlo data for super large sequence sizes. And in 1D, we have the MRG. And we're going to include frustration to basically see how far we can push the methods beyond what you can do with Monte Carlo, for instance. Examples of variational wave functions you're familiar with are, for instance, the Jasper wave function, which is just a simple exponential. And this is a physically informed wave function, right? So this is something that we extract from mean field or from spin wave theory. We extract the functional form from our analytical calculation. We plug it into the variational Monte Carlo. And we just play with these coefficients alpha here in the exponential, right? This is all work by Sorella, where he showed that, there's some classic papers by Hughes and Elser and others, where they show that actually this simple wave function with even one variational parameter and scaling those as 1 over the distance between two spins, approximates the exact wave function surprisingly well in 2 dimensions. Now, another wave function that you are probably familiar with is matrix for states. This is basically the underlying structure of the wave function in the DMRG, the density matrix normalization group method. It's just each coefficient is given as basically the trace of a product of matrices. And these matrices have certain dimension, and the matrix elements are basically our variational parameters. The nice thing about this formulation is that everything can be done algebraically. we don't have to do any Monte Carlo. We can just diagonalize matrices, do singular value decomposition, and we can solve the problem pretty much exactly. So the challenge, as I mentioned, is to go to higher dimensions. Matrix velocities don't work really well in higher dimensions. We want to do fermions in higher dimensions eventually. To do that, we are inspired by the original idea of Giuseppe Carleo and Matthias Streuer, of course, we all are familiar with by now, which at the time it was to use this very simple construction, the restricted Boltzmann machine. The restricted Boltzmann machine is nothing else but a sort of generalization of the Jastrow wave function. So we have our physical spins. This is a visible layer. This is where our physical spins live. This degree of freedom can be 0, 1, or up and down. And we have a hidden layer where we have some hidden spins that can also be up and down. And this is kind of the ancilla construction that you may have heard of. But the thing is that because of the particular structure of these the activation functions and the wave function here, we can exactly trace out the hidden layer and get a function of only the visible degrees of freedom. So the coefficient now is the same as in the Jastrow wave function, is the exponential of some energy. And this energy is a classical energy, and it's the energy of basically an Ising, classical Ising spin model, where all spins in the visible layer interact with all the spins in the hidden layers with certain weights tab. And you can sum directly over the biases, and you get basically the product of cautions. And this function is very easy to evaluate and surprisingly very powerful. Of course, this is a very basic variational wave function. Now people have tried all sorts of more complicated wave functions. We're going to use this one as a sort of toy example, but all the ideas I'm going to present today can be generalized to any neural network quantum state. Yes.
Here, the amplitude of the wave function is always non-active, semi-positive.
Yes. So not necessarily. So we can put all the weights to be negative. Sorry, complex.
Oh, complex.
So we use complex weights. So that's the thing. In order to introduce quantum mechanics, we have to use complex weights. So that way we can get negative coefficients. Otherwise, it would be only positive. Yeah, correct. So the variational solution is just plug into variational Monte Carlo, and we solve, right? So this is just a straightforward application of importance sampling. I'm not going to get into that. The optimization can be done in several ways. I want to, I don't want to bore you with the details, but I want to mention this briefly. There are two ways to do the optimization. So what you need to do is to find the parameters alpha that give you the lowest possible energy, right? The best variational energy. And that's our best approximation to the exact wave function. Straightforward application of the variational principle. Now, here we don't have a big data set. So that's the main difference with the machine learning 101. What you usually what usually comes to mind when you think about machine learning. So here we don't have data. We generate configurations, spin configurations in this case, to sample the energy, and our cost function, which is usually the distance between the data you want to approximate and the data you generate, is the variational energy. So we're minimizing the variational energy with respect to these alphas, and the way we optimize it is either by doing some conventional gradient descent or other more sophisticated algorithms such as Adam. But in general, in the context of quantum many-body systems, the best method is the so-called natural gradient descent. And I'm not going to get into the technicalities. This was a method that was originally proposed by Sandro Sorella. He called it stochastic reconfiguration. In the machine learning community, it was known by different name, natural gradient descent. But in a nutshell, what it consists of is of time evolving the wave function in imaginary time. So one can formulate this problem from a machine learning perspective, but when you map it to a quantum many-body problem, it turns out that it reduces to nothing else but time evolution in imaginary time. So basically, what you're trying to do is follow the wave function in imaginary time and eventually project it onto the ground state. So the and this concept it's going to become very important next when I tell you how we do thermodynamics. So geometrically, this can be interpreted the following way. So imagine that all your variational states live on this manifold, this curved manifold here. All the restricted multiple machines can represent only states living on that manifold. If you move away from that manifold, you can no longer represent it in terms of an RVM. So what happens is when you hit the wave function with the evolution operator, it will take you out of this manifold. It's no longer an RVM. The new state, when you apply the evolution operator, it's just a linear combination of RVMs. So what you have to do is project it back onto the RVM manifold and follow the path on the RVM manifold. And that will give you, well, that's the main source of errors, right? So if you could, if all your wave functions live on this manifold, you do the exact trajectory, and eventually you have to worry about anything. But the nice thing is that this path will always take you, no matter what, to the best possible state with the lowest possible ground state energy, at least within the variational manifold. And this idea that you can get away of the variational, out of the variational manifold and project back is going to be important next also. For instance, one way you can increase the expressivity of the wave function or the accuracy of the variational ansatz is by restoring symmetries. For instance, you know that your wave function has rotational symmetry on the lattice, has translational symmetry, and you can put that explicitly into the wave function by just applying translations with the corresponding refactors and rotations. And this new wave function here, after you do that, is a linear combination of RVMs, which is no longer an RVM. Or if you will, I mean, I use RVM for the neural network quantum state, but it could be any quantum state. So once you do a linear combination of neural network quantum states, it's no longer a neural network quantum state. So it's something more complicated that has more expressivity. So another way to increase the accuracy or the expressivity of the wave function is to do a couple of anxious steps. So what we do is we apply the Hamiltonian. So we hit our state with the Hamiltonian, we generate a new state, and now we have two RVMs. And now we do a linear combination of these two RVMs to get yet a lower energy state. And this is something that people used in the 90s, Sandro Sorella, Dagoto, and others. And one thing about being my age, I guess I identify with many of you, is that we know much of the literature before 2001. After 2001, everything exploded. I don't know, just my brain capacity. I don't know, maybe I'm getting senile. But anyway, so but the good thing is that, and the interesting thing also is that many of the young people don't know any papers before 2001. So I have an edge. I still have an edge. So what we did is first we play with these ideas, and we show that by applying restoring the symmetry and applying Lanczos, we can beat other methods such as other models such as convolutional neural networks and more sophisticated techniques. So what I'm showing here is just the relative error. This is the J1, J2 model in 2D compared to the exact result on the 6x6 lattice, which can be done exactly with exact normalization. And you see that our results with the RBM. So this is a convolutional neural network. This is the plain vanilla RBM, and this is the red dots are the RBM after a couple of Lanczos steps. And here, well, this is kind of like a crowded plot, but the circle, the black circle, and the blue squares are exact data points, and the lines that interpolate are actually from our neural network quantum state. And that's for 6x6, and the green and red curve are for 10x10. Okay, this is just to show that we can get state-of-the-art numbers, actually. Okay, so moving on, the title of my talk was thermodynamics and spectral functions, so I want to tell you a bit about that. So there are a lot of groups around the globe doing neural network quantum states nowadays, focusing on trying to get the best possible ground state and the best possible ground state energy, as I showed earlier. But when you do experiments, you don't measure energies. You measure some order parameter, maybe some correlation function, but also you look at spectra. So thermodynamics. So this is where I want to go next. I want to sort of present a couple of ideas to be able to produce data that can be directly compared to experiments. So one is to use, well, these are basically variational calculations, and we know that DMRG or tensor networks are also variational methods. And people have tried everything with DMRG for the past 30 years, right? And I know the DMRG literature pretty well. And so I thought, why don't we try to do the same with neural network quantum states? That's in a nutshell our reason. And so Steve White proposed this METS method, which is minimally entangled, typically thermal states, to calculate thermodynamics using matrix flow states. And a Japanese group proposed using this typicality-based method, which is very similar. And the idea is to start basically from a random state, evolve it in imaginary time to zero temperature. And of course, if the overlap with the ground state is non-zero, then you're going to end up in the ground state. So you do that with many, many initial random states, you average, and you get a very good description of the thermodynamics. So basically, you start from product states. The product states can be represented exactly in terms of a restricted Boltzmann machine by picking those weights. And then you just start from the product state, you evolve it in imaginary time using natural gradient descent, which is basically what we've been using all along to get the ground state. And we average. This is what we get. So this is the average energy over many, many initial random states for 6x6 and 8x8. And I'm comparing to exact quantum Monte Carlo data from undersampling. And you see that the agreement is fantastic, right? Of course, this is a wide range of energies. If you zoom in, you're going to see some wiggles due to the numerical errors. And of course, if you focus on this low energy region, you're going to see more deviations. And I'm going to show you in a second. So the energy looks very good, but when you calculate specific heat, you want to calculate the derivative of the energy, and that's when things get a little trickier. So that's where you start seeing some deviations from the exact data, but so far so good, right? So it works pretty well. So down here, what happens is that our RBM gets stuck in the ground state guess. So you cannot go any longer to the actual ground state. We can calculate magnetic susceptibility, as shown here, and we can do this in 1D and 2D. So these are proof of concept calculations, and but the method is general, can be improved. You can use a different neural network model, and you can it doesn't suffer from the design problem. So now we have a variational way to calculate finite temperature properties of quantum many-body systems. In the next few minutes, I want to tell you about how to, so I'm switching gears now. I'm going to tell you how we calculate spectral functions with variational Monte Carlo. So basically what we're trying to calculate is the imaginary part of the 2-point correlation function and the frequency. And so we're going to do it for spin Hamiltonian. So we're going to apply SESE, and we're going to have the 1/h in the middle. And the idea is to represent the Green's function in terms of Boltzmann machines or neural network quantum states. So one approach that comes again from the DMRG literature is to use what the so-called correction vector method. So the correction vector method consists of, you first have your variational state. You hit with the operator you want. Let's say the spin operator. Here, you get a new state. You encode that in terms of another variational wave function. And then you solve this equation, 1/h applied to that state equals to this. And that you encode it also in a neural network. And then you calculate the overlap between these two, and we'll give you the Green's function, the quantity you're looking for. The caveat, though, is that you have to do this for every value of the frequency. So the frequency enters to C here in the denominator. So you have to do this optimization for every value of the frequency. So you have to do zillions of variational Monte Carlo calculations, one for each frequency. And but we can do it on a cluster in parallel. So the variational optimization is very similar. Just minimize the distance between the target state and the state you generate. And this is the benchmark. So this is for a small spin chain with 10 sites. The referee asked us to show a plot like this, and you can see that basically it's right on top. It's 1-to-1 correspondence. We get amazing agreement. Of course, if you go to larger system sizes, things start looking a little more shaky. There are a lot of numerical artifacts, especially higher energies. But when you see a spectral function and a new method, you have to see cuts like this to be able to really judge how good the method is. Because you can plot it like this, and you won't see any of that, right? It looks beautiful. So this is dynamical DMRT. For the unfrustrated case, frustrated, variational Monte Carlo using this technique for the two cases as well. And the agreement is very good, at least in the color plot. Another approach, also coming from the DMRG literature, is to use Chebyshev polynomials. And I'm not going to bore you with the Chebyshev polynomials, but basically, Chebyshev polynomials are just an orthogonal basis set that, it's basically a sort of generalized Fourier expansion of the density of states. That's what we want to do. It looks like this. So this is a spectral function you want to represent. It looks like this in terms of the Chebyshev polynomials. These coefficients mu(n), which are your Fourier coefficients, are called the Chebyshev moments. And we have to calculate all these Chebyshev vectors, which are basically, so we start from the ground state. We apply the operator we want to estimate for the spectral function. And then we apply the Hamiltonian once, twice, 3 times, so on and so forth, basically following this recursion here. And each of these wave functions, T1, T2, Tn, is a neural network, a quantum state. And once you calculate all those neural network quantum states, say you collect 40 of them, 60 of them, 80 of them, and you plot your spectral function, you see how slowly it starts approximating the exact result. And this is actually an exact comparison for spin chain. And you see that the agreement is even better than the previous approach that we used before. The correction vector. And this is, again, a plot showing the spectral function using dynamical DMRG, restricted Boltzmann machine, and the correction vector. All right, I think I'm ahead of time. We can do this in 2D. This is again for 6x6, where we have exact data to compare to, and the agreement is pretty good, except especially at low energies. High energies, things start getting a little deviating from the exact data. And these are artifacts that are well known to occur in these methods. All right. So finally, to conclude, I just describe several methods to calculate thermodynamical properties and spectral functions, strongly related systems using neural network quantum states, using variation Monte Carlo. The nice thing is, of course, is that these methods do not suffer from the sign problem, and they are very general, so you can use any ground state wave function you want. For instance, this morning we saw this talk by Shui on the two-dimensional electron class. You can try this and look at the spectral function, for instance. The only limitations are the expressivity of the wave function you use and the computational cost of optimizing this wave function. But the potential, I think this method has a lot of potential. One idea is to combine neural network quantum states with Spectral factors, for instance, as we saw this morning. And that way you have less variational parameters and increase the expressivity of the wave function. And extend this to fermions, of course. And with this, I want to thank you very much for your attention.
Questions for the speaker? Alan? For scaling up the bigger systems, do you have a method for doing smaller lattices and then stitching together and then minimizing, or does that?
That would be nice. That falls into the spirit of coupled cluster methods, or if you will, large language models, where you have each cluster is like a word in your sentence, and actually we're working in that direction right now. Yeah.
Time for one more. Anybody have one? Yes.
So is it easy for you to plug your wave function into a wave function like
Well, this wave function in particular is trivial. The one we use here for these calculations is instead of your Jastrow wave function, you put a different expression. It's just
so
it's still though, yeah. I don't know how it's in the case of fermions how you may have to think a little harder how to, but that the sign and the phase is taken care of by the Slater determinant in front, right? So
that's what I thought.
Should be straightforward, yeah.
That brings sort of to the entertainment values. I wanted to push back a little bit on how you kind of framed, I guess on page 2, the problem, the contrast of QMC with the sign problem versus DMRG versus variational wave functions. To me, it seems like they're all just methods that have different aspects, different disciplines.
Yep.
If you can do this variational wave function, feed it into a QMC that has a sign problem, you will get an answer that's better than this variational wave function itself, and certainly better than the regular methods for sign problems. So then, why is it that we're singling out the sign problem and not emphasizing physical or just entity design? I guess, but it is for people who don't pay attention to this an important message to say whenever there's a sign problem, we should stop because there's a sign problem. But one could focus on, for example, DMRG doing cylinders, as we heard earlier, a boundary condition problem. So I guess my point is, it seems to me the sign problem is just a problem. right? Just like any other methods that have other. So I don't quite understand this framing of how that's a fundamental problem versus, you know, going up in bond dimension is a problem as well. Like,
Yeah, I see your point.
I'm
Every,
trying to be provocative.
no, every method has a systematic bias, and, you know, there's no, yeah, it's on the eye of the beholder. I guess, you know, people have their own biases, when they say, I prefer my bias to your bias. Right?
Okay, let's not,
Right.
that's a good place to stop. Let's.
All right. Okay, thank you.